It's 2 o'clock here on December 12th, 2023. This is the Mars Society Ambassador Program. I'm James Melton, Chief Ambassador of the Mars Society, and our mission is to serve as a team of professional people dedicated to elevating public awareness of our mission to land humans on Mars within this decade and begin settling the red planet. And we have 17 esteemed ambassadors focused on this issue around the world. 42 ambassadors in 17 countries, some of whom will be on the program now, and others may join us a little later, and certainly on the rerun. But we have a gentleman going to be talking with us today, and I'm excited about this as I've known this man for quite a while, and I want to give him a little introduction here so we're all familiar with what we're about to hear. Phil Hawes has been a leading pioneer in alternative design and construction for over 40 years. He is one of the most knowledgeable and dedicated green architects on the planet. He was the master architect for the Biosphere 2 project near Oracle, Arizona, which is near I believe it's north of Tucson. Phil is an architect whose area of expertise is sustainable and community development. He has established sustainable design educational programs in architecture and community planning in the US, Portugal, France, and has lectured worldwide on these subjects. Phil studied with Frank Lloyd Wright at Taliesin West. He holds a BA in architectural design and a PhD in sustainable community design. But the big thing that I know Phil Hawes for is he and my wife Dana share the same birthday, May 20th. So without any further ado, let me turn the platform over to my friend Phil Hawes, who's going to talk to us today about the Biosphere 2. He's going to talk to us about issues, major and minor in that particular issue of Biosphere 2. And I'm interested in hearing what he has to say and how that relates to Mars. Phil Hawes, you're on. Go for it.
Yeah, I think I didn't lose you there. I just uncovered you. There you go.
Right ahead.
Okay. Well, I suppose I hope that everybody has a rough idea of what Biosphere 2 was, what it looked like, and so forth. But Rick, if you could drop that first slide in, I'd appreciate it. This was what Biosphere 2 looked like in 1991, right after it was completed. And the main structure here is about 800 feet long, but that doesn't matter much, I guess. The two round domes are volume pressure compensators. In other words, when the sunlight hits that glass of Biosphere 2, it warms up the air inside, which expands and has to have some place to go. And so it goes into these two big domes. And over to the left side is the power plant, the electrical generation plant. I'm not sure if you can see my cursor. This is the habitat portion. This is the agriculture. This is the rainforest. This would be covering the ocean and the savanna. And then this is another shot of it in 1996, when under Columbia we were building in the foreground, building student housing for about 200 students that they were sending there. The building has got the black roofs on it there, was being re-roofed. Again, that's the electrical generation plant. Thank you, Rick. And this is a spin-off from Biosphere 2, which was sponsored by the External Tanks Corporation. They asked us to do a reduction if we wanted just to put two people into the oxygen tank that the shuttle used to ride up. was it possible to do that? And so this is the design we did for that reduction down to 2 people instead of 8 people or to 10 people in the large biosphere 2 itself. But after doing that, we had wastewater treatment system in here and water reclamation system, small laboratory, and space for 2 people to live. Okay, well, if we're going to go to Mars, first of all, the Biosphere 2 project had 2 purposes. One was as a test bed for going to Mars. We were very interested in going to Mars back in 1985. So it was obvious that not very much was known about planet Earth and how it actually functions in 1985, even though many ecological books had been written. It was 1958 before the Odom brothers wrote their treatise, their book called The Fundamentals of Ecology. And so it was really still a new field, and just the surface had been scratched as far as how did things operate in planet Earth. Nobody had ever built a big closed container, put a lot of species inside to check out these ideas and these relationships. So that's what we did. And we had 3,800 species roughly inside of plants and animals. That doesn't include the bacteria and the various small, microscopic animals that came into the biosphere just automatically through the ocean system or through the soil bacteria itself.
3,000 species, my gosh.
About 3,800, we think.
Okay.
Those are the ones we counted. Then there were a lot more. For instance, we actually had an infestation of octopus at one point because they're very tiny when they're babies, and they came in with the ocean water we imported from La Jolla, California. So we had to go in there and rout these guys out because they're a predator species. They were eating all the fish, and so we had no predator fish in there because we had only agricultural fish.
Now, let me just verify this. This is a totally closed atmospheric sphere, correct?
Yeah, the Biosphere 2 was atmospherically closed. Yeah.
Okay.
We had between a 6 and 10% leak rate. It was somewhat pressurized so that if there was any leakage, that the air would go out rather than air coming in, and then we would make up that air by putting in air that had been run through HEPA filters.
I remember being in the lower quarters of that biosphere, and they had this the rubber or whatever it was breathing device, that huge what did they call that? You know what I'm
Yeah,
referring.
we called them lungs, although they weren't really lungs, but that in the lung was a 90-foot diameter aluminum pan that was connected to this hypalon membrane you're talking about. And this would go up and down as much as 16 to 20 feet a day with the variation in the temperature and the volume of the air inside. And so those are those 2 big white bubbles that I showed in the slide. But
Okay.
inside of each of those was this pan going up and down. And we also had a 250,000 gallon reservoir water tank in there, which supplied the water, the basic water, although we recycled 100% of all the water and ran it through the atmosphere and back into rain inside.
Okay.
Yeah.
All right. Inside. How about that? That's interesting.
It was all done inside. My favorite piece of equipment in there was the nitrogen extraction device, which took nitrogen out of the atmosphere inside and liquefied it. And then it was used in the laboratory we had inside. And then as it was boiled off, changed back into vapor, went back into the atmosphere, then this piece of apparatus would pull it back out again and liquefy it, and round and around and around. That was my favorite piece of equipment in there.
Okay. All right.
So the second purpose, of course, of the biosphere, other than actually investigating how the ecological zones of the planet worked was to prepare ourselves to go to Mars. So that was the second reason that we built the project. And then the spinoff that I showed you briefly of the oxygen tank from the shuttle was what we would try. We wanted to put one of those up into space. There was a corporation developed by a bunch of people that thought it was rather expensive and wasteful to throw away the shuttle every time, or the oxygen and hydrogen tank every time the shuttle went up. Cost something like $100 million.
Could have had a V8.
So they thought this was a little wasteful and they wanted to put up something that could be tethered. Two of those oxygen tanks could be tethered together and rotated around and around so that they would produce a small amount of gravity and be a lot easier to work in space than having to float around and do everything.
If I may ask you,
Excuse me?
no, go ahead.
They took a cable up in one of the experiments, one of the shuttle experiments, and it was like a big backlash that when the cable was on a coil and suddenly it got away from them, and it was like when you're fishing with a fishing rod and a reel, and the reel goes faster than the line is playing out, and you get what's called a backlash, which is this incredible tangle of string on your line, except in this case, it was a tangle of cable. And so that particular experiment never was repeated. They just gave up on it when they had this one accident, which is too bad because to tether two of those oxygen tanks together and then rotate them around maybe a kilometer apart on a cable would give them enough give them a little bit of gravity there so that they didn't have to just float around all the time.
Sure, yes. And you did create, if I'm not mistaken, was it adjunct to NASA, a capsule for two people that was either going to the space station or designed to do such? And if you would talk about that just a little bit, and does that have any relation to what Robert Bigelow is doing? Are you familiar with Robert Bigelow in Las Vegas?
I'm
Who
not.
has created some space capsules that are attached to the ISS right now and being used. Their environments, living environments.
Right,
So,
but I'm not quite sure what you were referring to that we were involved in. We had a test module, but we didn't actually put anything into space. Our
oh,
test
okay,
module was done before we built the big one.
okay, all right, fine,
Yeah.
okay. So,
We had somebody living in there for 3 weeks maximum. It was also sealed up.
okay. How many people were in the biosphere too?
There were 8 people, but it was designed for 10. So we were figuring that maybe the president would like to come and take a few days inside just to get away from it all, you know.
And
But
why not?
that never happened.
Yeah. Well, forgive me for stepping in. Just continue, Phil.
No. Well, let's move on to the other slide, Rick, of the Mars sphere, because what we were doing with respect to the biosphere was bringing everything together at one time in one place. That a lot of different people had done smaller experiments, but not anything as closed up as much as what we did in the biosphere. And it became very apparent that if we were going to go to Mars, we were going to have to do something similar to that. At least it was apparent to us. Instead, on the planet Earth before going out and going to Mars. And so, what I designed in 1991 was this big 300-foot diameter sphere that would be essentially a vacuum, since the air pressure on Mars is about what 1/100th of what it is on planet Earth. So this is actually thought of as a ferrocement sphere. So could you give the next one, Rick? It's also surrounded by the town that would be the support town with engineers and different people involved in it, or just ordinary people who wanted to live near something like this going on. So inside, you can see that right in the center of it is the oxygen tank for the shuttle. It's about 60 some feet tall. And then down beside it would be a rover. There's a greenhouse in there. And underneath the regular, there's about 30 or 40 feet of regolith there with a machine called a subterrane. I just copied that after what they designed up there in Los Alamos, which was an electric burning device that would burn its way through solid rock and create a somewhat glazed tunnel behind it, because everybody's pretty much agreed now, I believe, that we're going to have to live underground on Mars or the moon due to the cosmic rays, penetration, all that sort of thing. And then below the regolith was the support system for this particular experiment. Overhead was a xenon light to produce the right kind of lighting, and inside it would vary from say 100 degrees below zero at night up to maybe 32 degrees Fahrenheit in the daytime at the equator of Mars. So when we did we did the design at least for a Mars sphere, so-called Mars sphere, to simulate going to Mars. And recently, the biosphere has been turned into the test module for the biosphere has been turned into an astronaut analog for going to Mars. And they're not running it in a totally closed environment simply because of the insurance issues involved and all that, and putting people into a remote atmosphere, such as Biosphere 2 was, of course. But people are a little more worried now about things like for short visits of 6 days or so, which is what they're doing now. They don't want to go through the issues of insurance to protect against people getting sick and thinking it was because they were in this closed system and so forth. So it is simulated, but it's an analog, but it's not truly closed up. And the test module is an international venue now for people that are interested in spending 6 days in a simulation of a Martian environment.
Now, is that just anyone or scientists or students or paid participants?
Seems to be a mixture of those types of people, and they have had what they call, I think they're calling them inclusions. They've had at least two, maybe three groups of people go in since when I was there in May, and I gave a talk on this particular project that they had.
Does Columbia University still have a hand in this project?
No, Columbia left the project in, I think it was 2003, 2002, something like that.
Okay.
The University of Arizona now owns Biosphere 2.
Oh,
And Ed Bass, who financed the initial construction and design of Biosphere 2, has put money in annually to help support the system. I don't know exactly what he's doing right now in terms of that, but it costs quite a bit just to keep it heated and cooled, you know. Although it's not a closed system anymore, the Biosphere 2 is not a closed system, but it still requires heating and cooling and so forth. It's
all right.
several $1 million a year just for that. Yeah.
Okay.
So, Rick, if you drop that other slide in, we could. This is a project that was actually students of mine did back in 1997 at the San Francisco Institute of Architecture out in San Francisco. I gave them a program for a town of 5,000 people, and that was based on certain sustainability principles. And the students built a model of it. This is what they came up with. And so this is what my particular thrust is, that if we are intending to go to Mars, we really need to solve our sustainability issues on planet Earth. And this has not been done at all. There's nothing that we do in any of the vital things that human beings are involved in, whether it's transportation or water or sewage or purification of air or food production or energy production. None of these things are we truly doing in a sustainable way. And so in order to address that on planet Earth, we need to start creating um, this particular sort of a ecological community is, I have chosen the number of people at 5,000. And this is based on certain things that people have written, and also certain economic principles and this sort of thing, that a town of 5,000 people is large enough to sustain its own transportation system. It's large enough to sustain its own medical system to a certain extent, and so forth and so on. So this is just something I'd throw in here, because we can't go anywhere and be sustainable if we don't know how to do it at home. Next,
That makes perfect sense.
could you give us the next slide, Rick? So getting into that briefly, this is in New Mexico where I am now. In fact, I'm in one of these houses, and these are all adobe houses. So one of the things that we need to work with is materials and methods of construction. There was a very famous Iranian architect named Nader Khalili, and when I attended the Case for Mars conference in Boulder, Colorado, back in 1985 or so, Nader Khalili gave a talk where he thought that we would be able to do lunar and Martian buildings using rammed earth. And at the time, I thought, this guy is really out of it. This guy is really too far gone, off the wall. But in retrospect, one of the first designs I did for the Biosphere 2 project, I was using rammed earth as the structure for the habitat, the part of the habitat that wasn't glass. And I still think, upon rethinking this over and over again, I'm pretty sure that we would have been able to make it airtight as was the one that we built out of steel.
That's
And
that's wonderful. I'm glad you brought Nader up, Khalili, because Dana and I met Nader. We went to one of his workshops actually in Hesperia, California,
right,
and he demonstrated various buildings that he had created with the rammed earth concept. I
yeah.
thought it was fascinating. Thanks for bringing that up.
Well, I truly believe that rammed earth could be done tight enough, and of course you'd have to make it thicker than an ordinary adobe wall of 14 inches or so. But I'm pretty sure that we would have been able to match, if not even beat, the leakage rates that we had on that.
Okay.
Put the next slide, Rick. This is typical of the houses here, and you can see. Let me tip this back for you a little bit so you can see around. This is it. I'm inside one of these houses at the moment, and it's got the vigas in the ceiling, and the walls are 14 inches thick. This is one of the smaller units. This is a 2-bedroom, 2-bath unit. And of course, the eternal fireplace that everybody in Santa Fe pretty much has fireplace, because it does get cold in the wintertime. Next slide. And as part of the sustainability, when we built this project, we had our own workshop, we had our own ceramic shop. The floors were all brick, which is a high embodied material as far as energy is concerned. But on the other hand, a brick will last almost forever, a couple thousand years easy. You can recycle these brick floors that are in this house. The houses are all heated with radiant heating systems, pipes in the floors, putting hot water through it. Those are easily retrofitted to solar heating, and the adobe itself is local material from right around Santa Fe here. So this is an approach anyway to the buildings and the methods of construction, the materials and methods of construction that you have to think about if you're intending to be at all sustainable. This is what it's going to take. We have to think in terms of true sustainability. and which kind of gets us to a definition. One of the main problems with sustainability is that people don't bother to look them up in the dictionary, look it up in the dictionary. So I did that, and the composite definition that I've come up with is that for something to be sustainable, it must be able to support and maintain itself indefinitely, without interruption or failure, without weakening in power or degradation in quality, while conserving an ecological balance that avoids depletion of natural resources. And the key word to sustainability has to be maintained indefinitely. And the indefinitely is an indefinite number. So I've just picked 1,000 years. If something that you're doing cannot be done for 1,000 years without depleting the environment or messing up the ecological balance or destroying the natural resources that maintain us, it's not sustainable. And so all the things you hear of out there in the quote real world about we're doing this sustainably and so on. So check it out. Almost 100% of the time, they're not sustainable at all. They can't do that for 1,000 years. There's no way. Another very nice, elegant definition of sustainability is one that David Orr, who is head of the Oberlin College Environmental Department, and he was the author also of Ecological Literacy. He says sustainability is the integration of human settlements together with nature so as to meet the requirements of humanity in ways that preserve, upgrade, enrich, and evolve the biosphere. A sustainable society is one that can persist over generations, one that is for, excuse me, one that is far-seeing enough and flexible enough and wise enough not to undermine either its physical or its social systems of support. So we obviously aren't doing that, and we have to do that in order for us to be sustainable on planet Earth. And we have to be sustainable here at least long enough to support people to go to Mars and learn how to be sustainable there, because it's a whole new ballgame.
That is a new ball game. I mean, other than the definite lack of gravity, 1/3 the gravity, the atmosphere being only 1% that of Earth's, and the deadly radiation on board. Do you see any other challenges that might be occur when we go to Mars to build a sustainable habitat?
Well, of course, the soil, whether or not it has enough toxicity in it, it's going to be difficult to work with or not. But I'd say the water seems to be the most serious issue. Uh, there's not very much in the atmosphere. You can pull quite a bit of water out of the atmosphere on Earth, and almost any place now, in fact, it's becoming a big business where these apparatuses can withdraw atmospheric water. We did that inside the biosphere. We condensed the water out of the atmosphere and ran it around and around and around. But that was in a closed system, and but it's being done now here. But on Mars, that's a different sort of story. So the water thing, I think, is going to be the major thing.
Yeah, water is always an issue. It's one of the key ingredients, obviously, for life. And although Mars does have water, it's accessing it's the challenge. We have water at the polar caps. We have glaciers on even in mid latitudes on Mars that can be reached by with a shovel. But the total amount of water on Mars, pure water, is limited. What my research and Zubrin's research, as he indicated, is I think there is something like 3 million cubic kilometers of water on Mars. And that's not meters, but kilometers. That's pretty good source. An average comparison there would be we have about 30 million cubic kilometers of fresh water on Earth. So although it's there and we have underground lakes, et cetera, which they've discovered, but it's accessing that water. So that's that, as you pointed out, Phil, that is one of the key elements. What else do you see as an issue that we
Actually, I think that from what you're talking about, I have no idea really of the magnitude of the assumed water on Mars. But it sounds very much like they'll have to have enclosures to keep that water from escaping. And while they can keep it inside and recycle it inside, if you use any of that if you break that down and try to make hydrazine out of it or any rocket fuel or anything like that, then that's going to go out into the general atmosphere, isn't it? Going to be a little bit more difficult to capture that and bring it back than it is on planet Earth, where we have high percentages of humidity. I don't know. It's not something that I've really thought about, but I'm sure somebody must be, I hope, somebody must be thinking about that sort of thing. You can only burn so much of that and use it up, and it's re-released into the atmosphere of Mars. And then how do you get it back? I don't know. It's
Yes.
definitely a problem.
Yeah, it's an issue. Of course it is. Among other issues, you all are familiar with, I'm sure, the MDRS, which is the Mars Desert Research Station. We have one in Utah, of which Roger Gilbertson was commanding the mission 286, I believe. Is that correct, Roger?
Yep, that was it.
And you mentioned something, Phil, on legal issues and challenges in Biosphere 2 and what is needed legally to bring people in there. Roger, do me a favor. Give me some insight on how that's handled with the Mars Desert Research Center residents.
Well, they had a release and you sign it, like just like if you're going to camp or anything else.
Okay.
So, I didn't get into the fine print because I figured that it would only involve a lawyer, and that isn't usually a good waste of money. I have other ways I'd rather waste money.
Well, we had to do that, of course, on the ship that we built as well. Take people out in the middle of the ocean, never been on a ship before. They have to sign a release before they can do that. And the people who went into Biosphere 2 signed releases and so forth. So it's doable, but on the other hand, your basic institution has to be willing to go into that realm. And so far, the Biosphere 2 has not been the existing ownership, being the University of Arizona. They haven't been willing to take up that particular issue as far as this astronaut analog that's been created inside the old test module is concerned. It's sealed up, or it could be sealed up very tight, but it is not being sealed up very tight, and the atmosphere is not being regenerated.
I saw a presentation recently by NASA's head of planetary protection, who's based at JPL, and she mentioned the cultural factors, and she had a slide up of the 1950s and early 60s, and she said, given today's climate, we would probably send people into space before we sent monkeys and dogs, just on ethical considerations. That we would be willing to risk people before we would, oh no, we can't risk a dog's life. So it's a cultural thing that comes and goes, I think we're facing right now.
Yeah, well, that's a little surprising to me. But
yeah. Speaking of that, Phil, if you could shed some light on, I'm intrigued. I never really got any definitive answers on the team of people, the crew in Biosphere 2 that were there for, what was it, 2 years?
Yeah, they were there for 2 years, right.
Yeah. And how did the interaction of people work? How did they combine together? And were they from different of different ethnicities and cultures, or were they all
Well, slightly. We didn't have a broad spectrum of cultures or races or anything. We had a fellow in there from Belgium. We had Americans, of course. Let me think about it. We had Sally Silverstone, who's British, but there wasn't a racial mix in there. But here's the thing: who wants to go into a closed system for 2 years? You pretty much have to take whoever applies. We did have one guy apply who said, I feel that I'm qualified to go in because I've been in the penitentiary now for 6 years, and I know what it's like to be in a closed system. But we had to reject this gentleman on other grounds, of course, from than the fact that he probably would be able to survive okay in a closed system. But that wasn't all there was to it, you know. So, but as far as the ethnic diversity, we didn't have uh, a highly diverse population. I guess partly would be because the Biosphere 2 didn't get enough publicity ahead of time for people to apply ahead of time, because they had to go through a couple of years of training before we put them inside the Biosphere.
Yes,
So
yes.
this wasn't something you could just sign up for and a couple of weeks later pop in.
Were there other issues that were experienced, either major or minor? And were there any incidents where anyone were needing to leave?
Was wanting to leave, they could have walked out anytime they wanted to. They were sealed in with a little lead seal about like what you'd have on your gas meter. So
Okay,
so you could just open the door and it would pop the seal. There was nothing about that. No, they
yeah,
were in there because they wanted to be in there, and they stayed in there. And personally, the personal relationships, a lot of them were they developed very strong relationships. A couple of the people in there, a couple of the couples got married, and but on the other hand, there was quite a bit of friction. They fought like cats and dogs as well. So they were, I guess you could say, human beings in a closed system do things like that,
yeah,
and there you have it.
yeah. Certainly something to consider on the path to Mars, being 6 or 7 months. With nuclear energy, it probably come down to about 2 or 3 months. But that's a long time. And even in the MDRS, there are many things that happen in there. And um, Roger, what's the longest time someone has spent in the MDRS?
I have no idea. You know,
Um,
we were mission 286, and there was one mission that it was a two-part mission a few years ago. They were going to do 160 days in Utah and then an equal amount up in the Arctic. I don't remember, but you know, they've tried long periods of time.
yes, I know Anastasia Stefanova, our Russian ambassador, great gal. She's going to the Colorado School of Mines right now. She was participating in some extended uh, uh, experiments with the Russian moon capsule on Earth, of course. And they only had a limited crew, but they seemed to coordinate themselves pretty well. I think the human element of communication is going to be one of the major issues in this. We not only have the technological issues, but we have the human element to deal with. And the Mars Technology Institute, I know, Phil, I sent you a little something on that, and some of the rest of us know about that. Um, it is covering several areas. One is the biotechnology for developing a food and greenhouse issues and how to develop this on Earth so they can totally transport that onto Mars. There are two other issues that the Mars Technology Institute will be addressing, and that will be the labor issue on Mars. Will be extremely important, just getting people there to do it. Well, AI will take a role in that, probably rather strongly, so that we won't have the need for human labor, but a lot can be accomplished through artificial intelligence. And then, of course, the nuclear issue, how to develop nuclear energy in a clean way, if there is such a thing, and I think they're working on that, so that those two issues, the AI and the nuclear, will probably need to be sourced out. But the major focus of the Mars Technology Institute will be the biotechnology. But again, I'm more into the human aspect, not being a scientist myself, but more in the psychological realm of that. I see that Ashton Zeth is on the line here, and I just want to ask her a question. Are you able to answer questions, Ashton? I know you're on your iPhone. You could be in the car.
Can you hear me okay?
We can hear you just fine. You have a
I am in the car, yes.
Okay, you have a podcast. Well, keep your eyes on the road, gal. We have a podcast by Ashton coming up, the Red Planet Live next Tuesday, the third Tuesday of the month at it's 5 p.m. Is that Pacific time, I believe.
Yes.
And you have an astronaut coming on board. Is she going to talk about any of these issues, or do you have any idea where that's going to go, where the conversation will lead for next Tuesday?
Yeah, Dr. Shauna Pandya. We will be talking a bit about that. I've got a question specifically for her about, her experience at MDRS and the evolution of that and how that's going to be impacting in the future with MTI. Talking about the biological, like you mentioned, the psychological. She's working right now on some virtual reality for medical and bio. So yeah, all of that is going to come up in the conversation. I actually just chatted with her a couple hours ago before I got in the car. So yes, we will be covering that on the podcast next week.
Okay, great. You do a great job on those podcasts, by the way. I do enjoy seeing them, and you bring in some intriguing guests, as we have
Thank you
today
so much.
with Phil Hawes. Phil, any other thoughts before we open it up basically to questions to people like Ed and Roger and Ginger and Nasir, who's here, Ronnie Stewart, Story,
You mentioned,
Doc Matliff, Gar.
excuse me, you mentioned the nuclear issues, and I believe that there was a man named Bogusch, Bogusch, perhaps back in the 80s, who was talking about aneutronic type, something called aneutronic nuclear fission, and it wasn't supposed to have the same bad effects. And also, Bill Dempster, who worked on the Biosphere, he was our chief engineer on the Biosphere 2 project. He's had some thoughts on that. And so anyway, I'd throw that in there because I haven't followed up on it myself. I don't know what's happening.
Okay. This is your opportunity, all of you who are on board, to talk directly with Phil, ask him any questions. He's a very candid man, as you know. So let's hear from you. Just unmute yourself and come right in.
But Ginger, are you waiting to ask a question?
Right. I have some, thanks, Roger. My mic finally worked. So I have some questions about our Mars Institute, the university. I don't know how it works or who's like what stage, in which stage we are in right now. And also for Phil, because Phil mentioned about some applicants. I don't know like how like where the requirements for the candidates for the program.
Biosphere 2 is not being run as a closed system anymore. But as far as going into the analog, astronaut analog part of it, which is the old test module, which has been expanded, I'm not involved directly in that. But if you want to send me an email, just at philbhawes@gmail.com. My name is Hawes. So it'd be Phil, PHILB HAWES@gmail, and I can forward that to Kai Stats, who is more involved in that. He was the man who rebuilt the test module at Biosphere 2. He spent 2.5 years doing that and expanding it into this astronaut analog Martian system.
Thanks.
If you would like to do that, I'd be happy to transfer that for you.
Thank you, Phil. Who else has a question for Phil.
Yeah,
I
I've
do.
got
have- oh,
Is that Nasir?
well, John's unmuted here, but I've got one or two at some point. But John, go ahead.
Okay, John, go ahead. Yeah.
yeah, a specific question for Phil, and that was around the exercise with the population of 5,000 that he illustrated earlier in his talk. And did they come up with some ideas about in a self-sustaining group environment or society like you described? Was there a minimum amount of personal space that they discovered that was ideal for humans to be able to coexist like that, enclosed environment?
Well, the so-called eco villages or whatever you want to call those are not closed systems in this like Biosphere 2 was. Biosphere 2, we just worked backwards actually toward the human beings from the amount of area we allocated to the rainforest and the desert and the savanna system and the ocean and all that. We pretty much decided that, and the human beings part of it, the habitat part, grew. It evolved much more than the wilderness part did, or the agricultural part. Those were pretty much established in the beginning, or at least assumed in the beginning, estimated in the beginning. And what happened as far as when we started working on the habitat itself, it grew quite a bit. I can't remember the exact number, but I think it grew from something like, say, 6,000 square feet to 20 or 30,000 square feet, because we put in a machine shop and we had all that sort of support mechanisms for the human beings inside, and their repair work that they would have to do or might have to do on the biosphere itself. And we had that, as I mentioned, we had an analytic laboratory in there, which was no small thing. It was quite a rather large. So when you're talking about a town, that's a different idea from being closed. It can still be a huge sustainability issue, and is, but as far as being a closed system, it is not a closed system. And what I have used in my design is 440 square feet per person of house, not including the wall thicknesses, because if you're doing something like adobe, rammed earth, straw bale, anything of that sort, your walls are very thick. So I forget about, I don't include the wall thickness in the amount of square feet that each individual person would have. So they have 440 square feet in the house itself and another 200 square feet of external private open space, like a patio, a balcony, series of balconies, roof decks, whatever it might be. That's the number I use, and that's quite a bit less. No, it's about what human beings in the United States are now building their houses, but the houses here are going out of. They're really getting way, way, way too big. It's not as small as the houses, let's say, in the late 50s or the 60s, but it's more like houses might be maybe back in the 80s, 90s.
Phil, were some of the unintended consequences or surprises that the Biosphere 2 experienced?
Well, the big one was lack of oxygen. It'll really get your attention. And what happened was the carbon dioxide, since CO2 has O2 in it, but the carbon dioxide was being absorbed by the concrete as it cured. If you go through the cycle of curing cement, you'll see that it gives off in the beginning it gives off heat, and the CO2 is reabsorbed into when you burn the actual stone, limestone, to make the cement, you're burning it and carbon dioxide is going into the atmosphere. when you put water with that cement, and it also gives off a certain amount of heat, but it doesn't give off as much heat as it took to make it, but it gives off some heat, and it also reabsorbs carbon dioxide. So if O2 is in there, the carbon dioxide is reabsorbed into the concrete. And the other thing that was happening was the soil bacteria were it was very rich in carbon in the soil, because we realized that soil was going to have to produce the carbon for the growth of trees and other plant life in the biosphere. And we were assuming when we built it that it would be sealed up for 100 years. So we had to provide enough carbon in the soil to be able to grow trees for 100 years. And so both the soil bacteria and the reabsorption of the carbon dioxide into the concrete made a lack of oxygen. So they put oxygen inside. They brought a big truck up and pumped oxygen in, because the people inside were operating up somewhere around 14 to 15,000 feet elevation with respect to the oxygen that they had. Everything else was just like it was normally down there in Arizona.
Did hypoxia kick in and cause some uncoordinated activities because of the altitude or not?
People having a lot of trouble breathing at night, sleeping at night because of the lack of oxygen. So they had little machines that would give them some oxygen, but they had to pump in a bunch.
So unintended consequences raise their heads again. Yeah, forethought. Roger, go
Some
ahead.
some people said, well, anybody would know that. Well, anybody didn't know that. I didn't know that.
You
And
have to do the experiment for these things. Yeah.
Yeah.
Phil, thank you for this presentation. You know, I've been following your work for years without even knowing it, and it's wonderful to see everything you've been thinking about. Something I've wondered about, and in designing a Martian city, Mars is cold, and you know, a warm day on Mars is like a cold day in Chicago, but at night it's far, far colder. Is a Mars city going to need a heat source, or will it be generating enough heat? Say if you had a city of 5,000 people, all the activity that goes on, is it going to be a net heat producer? And how does that influence the fundamental design of whether you're building it as a radiative surface or a closed thing that's trying to maintain its heat?
Well, I've never tried to actually design a city for Mars, but I would assume that you'd be able to pick up quite a bit of heat from the sun, even though it's cold for sure, but the sunshine still shines, and I'm sure that they can pick up quite a bit of heat for heating water, or for photovoltaics or whatever you
Mhm.
might want to do that way. But I'm pretty sure that they're going to have to live at least in the beginning, and maybe for a long time underground, primarily
Yeah.
under.
Yeah, well, radiation protection, and then building the pressure, having windows then to allow the sunlight in. And every time I hear an initiative about, oh, we need fusion power, we need to do something else, you know, we have the perfect fusion reactor. We have the sun. It generates all its energy. It gives that energy to us for free. It's about 10 trillion times the amount of energy we currently use. So there's plenty of excess there. We're just not collecting it and using it efficiently. The idea of trying to make a little teeny sun in a factory somewhere, then I can sell it and put it through a wire to you, that continues to be a waste of effort.
But of course, Mars is quite a bit of distance from the sun, and with its elliptical orbit, it's to such extreme, one of the most elliptical in our solar system.
Mm-hmm.
It varies the size of the sun considerably. So I guess capturing that energy is the key element.
That's true. And basically everything, you know, we don't go to, as I've reiterated here many times, we don't go to Mars to escape the Earth's problems. We go to help solve them. And if we can live off of solar energy on Mars, it's, you know, twice as easy to do here on Earth, because we are that much closer to the fusion reactor.
By all means. Before our time runs out, I want to include everyone. I see that Kai has joined us from Ghana, West Africa. Are you there, Guy? Kai?
I'm here. I'm not in Ghana yet. I'm still around. I'll be leaving. I'll pretty much leaving like hopefully in January. So yeah, I'm still around. Yeah. Sorry for joining late. I was on another call. Yeah.
Okay, well, I'm glad you were here. I know you had a good stay with Roger Gilbertson and
Yeah.
you toured the United States a little bit, so that's great.
Yeah, it was an incredible host. Yeah.
Thank you for being on today, even if it was short. Um, uh, Nasir, anything from you?
Yeah, first of all, hi everyone, and thank you, Mr. Phil, for that wonderful presentation. I had one confusion and another question. The first was, I'm getting a little confused between the analog research stations and the biospheres. Like, how do they both differ, firstly? And second question is, how might the extreme environmental conditions on Mars impact the design and construction of habitats compared to the earth-based sustainable architecture that you showed in your presentation? Like, how would that differ?
I'm not quite sure I understood the second part of your question, but as far as the first part is concerned, the astronaut analog part of what's now Biosphere 2 is an outgrowth, but it's really not part of the original Biosphere construction or design. In other words, the original Biosphere, which we did back in the 80s and 90s, was to study the ecology of planet Earth, with the idea that that if you don't understand the ecology of the place you live, you can't very well go out someplace else and take living systems with you, because to go to Mars or to go to the moon, you have to take living systems, right? So you better understand what they are and how they operate and how they function. So that was the main thrust of the Biosphere 2 project, and it was a sealed up system in order to study these things. For example, nobody had ever studied, I shouldn't say nobody, almost nobody, except maybe Billy Wolverton, who worked for NASA for a while. Nobody has studied to any extent the outgassing of plant life. So that's something that Billy Wolverton started doing. He'd put plants inside of boxes, and then he'd put a little bit of acetone in there, and he'd see what the plant would do with the acetone. Use a gas chromatograph mass spectrometer to check it out. Did the soil bacteria destructure that acetone that was put in there, and so forth and so on? Or what did the plant output itself? What was the plant putting out as part of its living system? So these are things that have been very, very, very slightly looked at by anybody. There's no money in it. I've got news for you. There's hardly any money in it. People haven't been able to figure out any way to make money out of it. So it's a pure research sort of environment to do that kind of work, which is what we were doing with Biosphere 2. We were doing pretty much basic stuff that nobody wanted to do because there was no money in it.
Yeah, that's interesting because that's where the Mars Technology Institute and the Mars Laboratory Institute are generating income, or able to generate income through the Mars Laboratory Institute. And being a 501c3, the Mars Technology Institute can benefit from that and do the research. So that's one quagmire that I believe we're attempting to resolve, how you can actually generate dollars and cents while you're researching. Although I think anyone who does an investment in this must have a concept of a future vision for our civilization, must have a reason to do it, and some type of a philanthropist perspective. We're going to Mars, as we all know, and we're going to be going relatively soon, but we'd like to be a little more comfortable there when we go, to have things pretty much in place. Before I end this, I want to make sure everyone has had a chance. And by the way, Nasir, thank you. Nasir's from Pakistan. He's up late tonight. So
Yeah, it's just 4 a.m. here. Yeah.
4 a.m.
Hi everyone. Yeah.
You are a champion. You're a champion.
It's
Uh,
it's so good to hear you guys. I can stay awake all night. Yeah.
And I want to thank you, Nasir, for all of your correspondence, your videos that you actually send me. I play them. I've shared them with several people, and your top quality, your pictures are great. The programs that you're doing. God, I'd like to come over and attend one of your programs as well. So thank you all for all you are doing, and a special thanks to Phil Haas for taking his time to share his insights with us about his designing of the Biosphere 2 in Oracle, Arizona. It's something that we all need to know about. We can learn from each other as we're doing here. So if there are any other questions, last one, Ed, go right ahead, my
Yeah,
friend.
Phil, your email again, before your first and last name, did you have the letter D? Is that part of your email?
B is in Bravo.
B is
Oh,
in,
B, not a
Yeah.
D.
B, yeah.
Okay, B.
I put it in the chat box
haven't-
there if you want to take a look.
I haven't
Yeah.
found that yet. Okay.
I
All right.
just put it in the chat box, everyone. Oh, yeah, both of us.
anybody wants to get in touch-
NASA and I both did it.
Yeah.
By the way, Phil, you and I have an indirect connection when it comes to sustainable architecture. I'll send you an email on that.
Okay,
My
great.
wife works for a firm in Utah, which is very, very big on sustainable architecture. You may have heard of them, GSPS. Maybe not.
Up on
Oh, They're
architects.
they're very big on that.
Yeah.
Okay, I'll send you an email.
Thank you. Thank you.
Oh, thank you. Appreciate
And-
your thought.
And
I'm done.
again, thank you all for being on board today. I found it very enlightening. We have recorded this session. I will be bringing it into a YouTube format here shortly. Actually, Dan and I are leaving for the rest of the week. We won't return until Saturday, so I won't be getting to it until then. But I really appreciate your presence. And all of you sharing your interest and the questions that you have. And Phil, again, a special thanks to you for taking your time to do this. And Rick Todd for being our tech man on set with the overheads. That was thoughtful of you to do this. So Jim Melton, Chief Ambassador to the Mars Society, Mars Ambassador Briefing, signing off for the moment. We'll see you next time around.
Thank you, James.
On to
Bye.
Mars.
On to
Happy
Mars.
holidays, everyone.
On to Mars.
And thank you, Ginger. Happy holidays to all.
Happy
See you
holidays.
next year.
See you
Stay
next year. Dr. House.
Bye.